Okay, we're going to go ahead and start. I hope everybody can hear me. And I just decided to leave the camera pointed at the stomach that I'll be showing to, it's not a real stomach, to the AP2 lab this afternoon. But anyway, we're going to continue our discussion on the nervous system today. Anybody have any questions on anything? I know that individuals are having trouble seeing their grade on their lab test. And I don't know why, because I see it. I see your score. I see it showing up in grades. I don't know why you can't see it. There's some switch thrown somewhere that I got to find. I'm working on it. Have no fear though. I do have your grade, and if I don't get it fixed, I'll just start sending out the grades to people. So I don't know why it's doing that. So anyway, are there any questions on anything? Okay, and I'm going to go ahead and go into our lecture, and we might even get done with this chapter today. So let me. Okay, we were talking about action potentials. We're always talking about action potentials, so that's where it's at. You know, in a nerve cell, the action potential is very similar to what we see in a muscle cell. We have a depolarization event that changes the charge on the membrane of the neuron. The resting membrane potential of the neuron is minus 70 millivolts. We open up sodium gates. Sodium rushes in, we depolarize. Threshold here is only minus 55, not minus 50, plus the resting potential is minus 70, not minus 90 like it is in a muscle cell. So we depolarize, and the charge in the membrane changes to all the way up to plus 30. And when it gets to plus 30, the sodium gates close and the potassium gates open up. And then we start repolarizing. And just like in the muscle cell, it is an all or nothing event. It either goes or it doesn't go. If you hit threshold, you go. If you don't hit threshold, you don't go. Minus 56 millivolts, too bad. You don't get the threshold. Minus 55 and below, you've hit threshold and you're going to run every time. Now the action potentials are all the same size. Every action potential we generate looks the same, because the action potentials don't mean anything. The action potential is just a wave of ions moving across the membrane, changing the charge from minus 70 to plus 30 and then back again. But it's what the action potential represents. Where is that action potential going? Is it going up into the brain or spinal cord, or is it going to another neuron or a muscle cell or a gland? If it's going into the brain, that action potential is coming from a special sensory receptor, and the brain knows what that means. Even though the action potential from a touch receptor looks just like the one from the eyeball. But where it's going and how it's interpreted is how we make it work. Yeah. So we hit threshold, and the voltage gates for sodium are going to open up. You know, we hit threshold when the ligand gates open at minus 55. Ligand gates open when a neurotransmitter lands on them, and they open up for sodium, and sodium comes in, and we get a localized depolarization event. And if we depolarize the cell body at the axon hillock to 55, minus 55, then we've hit threshold. If we hit threshold, then we have our action potential, and we will change the charge in the membrane all the way to plus 30. And you see that down here on the little graph. There's our resting potential, minus 70, threshold's minus 55. When we hit threshold, we shoot up to plus 30. Sodium gates shut, excuse me, sodium gates shut and potassium gates open. Potassium goes out, and we are repolarizing the membrane. Now we go all the way down to minus 90. We overshoot or undershoot, however you want to say it. We hyperpolarize down to minus 90 millivolts. And then we come back up to minus 70 at the resting potential. Why do we do that? We do that to give the sodium gates time to reset, because if you look at the graph, our sodium gates are wide open from 55 to 30. At 30, they start to close. And they close and they close and they close and they reset themselves and reset themselves and they continue to reset themselves. And the potassium is still leaving the cell membrane, still leaving the cell membrane, and we undershoot, making it harder, making it much more difficult for the, it's harder to depolarize a membrane that's at minus 90 than it is at minus 70. What the undershoot does for us is gives our sodium gates time to be fully reset, ready to go for a second action potential. Because when we undershoot like that and go all the way to minus 90, the charge in the membrane at the bottom of the curve there is minus 90 millivolts. That means if you want to try and stimulate another action potential, you don't have to change the charge from minus 70 to 55. You got to change it from minus 90 to 55. But then we recover, we rebound up to minus 70, and now we're ready to go again. What that dip does is gives us time. It gives us the time we need for the sodium gates to get ready for a second action potential. This is the hyperpolarizing phase here. So again, this is an all or nothing phenomena. If it starts, it's going to go. If it starts, it will run until it's done. It will not fade out halfway through. If we can hit threshold at the axon hillock, we will get an action potential every time. Now, the action potential will always run down the axon. It doesn't go backwards. It does not go backwards. It runs forward. It has nothing to do with the strength of the stimulus. If the stimulus gets you to threshold, you get an action potential. And it doesn't matter if the stimulus is a hammer hitting your thumb or tapping on your thumb with a pencil. If you can hit threshold with that stimulus, you'll get an action potential. The action potential doesn't care about the intensity, doesn't care about the strength of the stimulus. Now, we do pay attention to the stimulus strength, but the way we do that is increasing the frequency of action potentials we generate. So if we're getting a lot of, if it's a very powerful stimulus, we're going to get a lot of action potentials coming one after another, after another, after another. That's how we determine that it is a powerful stimulus. If they're coming at a slower pace, it's a less intense stimulus. The difference between smacking your thumb with a hammer, I don't know why you want to do that, and tapping it with a pencil, it shows up in how many action potentials you're receiving in the brain for touch and pain receptors. So we don't care about the strength of the stimulus with the action potential. They're all going to be the same. What's going to happen when a nerve ending, when a sensory receptor is stimulated, it will undergo a localized depolarization event. And if that depolarization event can reach the axon hillock of the nerve and be at minus 55, it will trigger voltage-gated sodium channels to open up, giving you an action potential.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
Okay, so our action potential starts and it runs till it's done. Now, the difference between myelinated axons and unmyelinated axons is speed. The myelinated axons will carry the action potentials very rapidly, 100 meters per second. But even at 2 meters per second for the unmyelinated axon, the uninsulated axon, if you only have to go a millimeter, 2 meters per second is still, as far as we're concerned, instantaneous. And most of the areas in the central nervous system where we have unmyelinated axons, distances between neurons is going to be very, very, very short. So we don't notice any delay. To us, it's all instantaneous. Now, something else that does matter is there are a few places where size matters. This is one of them. The axon diameter matters. Larger axons can carry the action potential faster than smaller axons. There is less resistance. Just like in electrical wiring, larger wires do a better job of carrying a current without any resistance. Resistance in electrical wiring shows up as heat. You wouldn't use speaker wire, and if you know how thin speaker wire is, you wouldn't use speaker wire to wire your house. You wouldn't have a house very long if you did, because the speaker wire would overheat. You also would not consider plugging plugging your computer or charging your phone with very thin wiring, thinner than what we have. But when we have your USB connections, we have to, in electrical charges, we have to have thick wiring to deal with current flow and resistance. We don't like to have a lot of resistance. Same thing in our nervous system. Larger axons send the signals better. There's less resistance to the movement. So we have large axons that are heavily myelinated, and we can move our action potentials down these axons rapidly. We have insulation, and it's a large axon, so there's less resistance, so the signal travels quickly. We also can use what's known as saltatory conduction as opposed to continuous conduction. With saltatory conduction, we leap. Salta means to leap or to jump. With saltatory conduction, we leap. Now, what are we leaping over? Well, axons that are encased in myelin. The myelin wraps around the axon in segments. It's almost like a hot dog bun wrapped around a wire. And you have a whole series of hot dog buns linked, stacked one after another in a row, and there's a gap between each bun. And the gap is called the node of Ranvier. And so in our myelinated axon, we can jump. The action potential actually jumps or leaps or saltas from node to node to node. So instead of having to run down the axon just one step after another, like a skeletal muscle does when it depolarizes and repolarizes, we jump from node to node to node, and our signal goes there so much faster. It's just 30 times faster. Speeds approaching 100 meters per second, or 30 miles, 300 miles an hour. It's pretty fast to go 3 feet or a meter or something like that. So the myelin sheath will insulate the axon. The myelin sheath doesn't allow any leakage of sodium ions or potassium ions out of here. The same way an electrical cord, a long electrical cord that's heavily insulated, does not allow the electrons to leak out, the charge leaking out. You would not take a 100-foot wire, a 100-foot extension cord, and strip the wiring off and plug it in one room and run it 100 feet to another room and then hook something up to it and expect it to work with just the bare copper wires exposed, because you would lose most of the charge that would be dissipated into the air. You wouldn't have anything when you tried to plug it in. So we insulate electrical wiring, we insulate our axons, the signal stays intact, and we essentially jump from gap to gap. Continuous conduction is just like it sounds. We have to go through every segment of the axon. We depolarize with sodium ions, and then we repolarize right behind them. The sodium gates open and they shut, and the potassium gates open and they shut, and each segment moves down along here. It moves down across the axon, and that takes time. Not a lot of time, but it takes time. So this is continuous versus saltatory. The example up on the top, if you press on that balloon on one end, the wave through the balloon represents the axon. It's unmyelinated, and it takes time to get from the beginning to the end. But if we can actually see the jumping where the gaps are down below on the second example, we see how much faster we can get down to the axon terminal. 30 times faster, generally. Continuous conduction is slow, but it doesn't matter, because the areas where we have continuous conduction, we only generally have to go very, very short distances. So for us, it appears instantaneous. We don't notice any, okay, I gotta wait for the signal to get there. Okay, it's got there. Now I can change my slide. So it doesn't work that way. For us, for our apparent view of a action, it's instantaneous. Now, there is a problem with the myelin sheath. Now, the myelin sheath is made of proteins and lipids. It looks like a white matter. In fact, we call it, it's what gives the white matter of our brain and spinal cord its appearance of white matter, the presence of the myelin. But there is an autoimmune disorder called multiple sclerosis that will attack the myelin sheath. We don't know why. We don't know why autoimmune disorders do what they do. Our immune system attacks the myelin. It destroys the myelin. It leaves a scar behind called a sclerosis. It's a lesion. A lesion is like an open sore that doesn't heal. Cancer cells, growth of cancer cells. We refer to that as a lesion also. So we have this lesion of destroyed myelin called a sclerosis. It calcifies, it becomes hard, and it stops carrying information. It stops allowing the depolarization wave to jump from node to node. And so we can't send our signals. We don't get these nerve impulses. We don't get these action potentials going down the neuron. And so we end up destroying the ability of the axon to carry information. And we grow more sodium channels and we lose them, we grow more and we lose them. And many times the signals go off in all different directions. And so we lose control of we lose general control of our muscles and our glands. For example, we have vision issues. We can have weakness in our muscles. We can have loss of muscle control. We have problems in speech. We lose control of our bowels and our bladder. But because it's an autoimmune disorder, it doesn't all happen at the same time. It depends on which organ system is being affected at the time. And then they go away. The autoimmune attack on the attack on your myelinated axons stops. You go into remission, and then it comes back again. And if it was attacking vision before, maybe now it's attacking equilibrium and balance. And then it comes back, and maybe it's attacking muscles, because it comes and goes. And you can't predict what organ system is going to go after next. You can't predict how long your patient will be in remission. And so, when we go into remission, we try to recover by generating more sodium channels so we can continue depolarization, and then we get attacked again. So how do you treat it? Well, immunosuppressants, which is a whole other area of concern, because if you're treating somebody with immunosuppressants, you're suppressing the entire immune system, which sets them up to, concerns about exposure to other pathogens. So now something else that is fairly recent, vitamin D. Vitamin D levels if vitamin D levels are maintained at a high concentration in the blood, it may prevent this from occurring. Don't know why. We don't know a lot about autoimmune disorders to begin with. We don't know what turns, we know what they do. We don't know why they do it. We don't seem to know why vitamin D can help to prevent the onset of multiple sclerosis, but it seems to. So, okay. Now something else. Okay, so there's one issue we have, and it doesn't happen often, but it's not. It is. I don't want to say it's a frequent occurrence of an autoimmune disorder, but it's not unusual for you to have patients. You may see a half a dozen patients in a lifetime of practice. Now, something that happens a little bit more frequently for us is the ability to block the signal of the action potential. If you've ever been to the dentist, if you've ever had dental work done, you know that before they do anything, they usually inject Novocaine or lidocaine into the jaw. Okay, have a good doctor's appointment. So don't let them hurt you. So, okay. Anyway, back to Novocaine. Now, some people are so afraid of dentists that they have to be Novocained in the car before they even go into the building. I won't say that I don't like dentists, but I've had some bad experiences. So what Novocaine does and lidocaine, it is injected into the area of a nerve called the trigeminal nerve. It has 3 parts to it. The middle part innervates the maxilla on each side, and the lower part innervates the mandible on each side. What lidocaine and Novocaine do is they block the sodium channels. So when you have dental work done, your pain receptors, if they're stimulated, are still going to respond. They're going to say, "Hey, that really hurts." I think and stuff like, "I think your dentist is enjoying this way too much, and it really, really hurts." But you don't feel that because the pain signals, the action potentials from the pain receptors are traveling up the nerve, and they hit the area where the sodium channels are blocked, and nothing happens. The signal doesn't get any further. But it doesn't just block pain signals, it blocks everything. If you've ever had Novocaine, you know, like the whole side of your face is numb. No touch, no pressure, no pain, no nothing. And then it gradually wears off. But it's how we block all the signals. We block all the sodium channels at some level up the nerve so that the pain signals can't get past that. So we don't get past the area where we have where they've been, as they say, anesthetized. So I didn't trip over the word. Whether we have, outpatient surgery, local surgery, maybe on your hand or on your, like arthroscopic surgery on your knee, things like that, we are simply blocking the pain signal so we don't feel it. This also happens to us on a much smaller scale. Who's ever had their foot go to sleep or their leg goes? Yeah, you sit funny. You put a lot of pressure on your leg indirectly, and you get up and your leg's numb, and you say, "My foot's asleep," or you sleep funny on your hand, okay, and it's numb. You are pressing on the blood flow. You're obstructing the blood flow going to that part of your body. And since our neurons are so dependent on oxygen and glucose, even interfering with the blood flow a little bit causes them to go numb. We alter the flow. Your hand goes to sleep, your foot goes to sleep. You're outside on a very cold day and your face is numb. Again, because on a cold day, what do? We pull blood away from the skin so that we don't lose a lot of body heat. So your face gets numb. You can't feel anything because we've temporarily rerouted the blood supply. Enough to keep the cells alive, but not enough for the neurons to say, "Hey, I can feel cold, I can feel pain." They're just numb. So and then you go inside and it feels better after it warms up. So this is, that's a much more generalized numbness, if you will, than what you would get with lidocaine or any kind of anesthetic. So same principle though, you're going to block the signals. So now, how do we tell? I alluded to this earlier. How do we tell how strong the signal is? How do we tell the difference between a light touch and a firm touch? If someone taps you on the shoulder with a feather and you feel it, or someone smacks you on the back of the head, and you definitely feel that. A light touch and a firmer touch. the action potentials generated from either touch are going to be identical. There's not going to be any difference in the action. You're not going to get a big action potential if you hit your thumb with a hammer. The action potential will be exactly the same size. There'll be no difference whatsoever. However, how do we determine intensity? Well, it shows up by how many action potentials do we generate. The more intense the stimulus is, the greater the frequency of occurrence of the action potential. There's no such thing as a weak action potential or a strong action potential. Let me say that again. There's no such thing as a weak action potential or a strong action potential. They're all the same. And it doesn't matter which sensory receptor they're coming from, they all look the same. But the frequency tells us intensity. The number of action potentials per second is the frequency. And if we have a high frequency of occurrence, it means the stimulus is strong. If we have a low frequency of occurrence, stimulus is weak. We're still getting action potentials, but we can tell the difference between a strong odor and a weak and a faint odor. We can tell the difference between a high temperature and a normal temperature. We can tell the difference between a light touch and a powerful touch. So we have the frequency of occurrence tells us the intensity. Because we certainly, otherwise, because the action potential, the individual action potential is not going to tell you anything. But even if we are sending rapid, have a very high frequency of occurrence for the action potential, each time we have the action potential, the neuron still has to depolarize, repolarize, hyperpolarize, and reset itself before it can go again. There is always a lag between each action potential. Now it's measured in milliseconds, but there's always a lag in action potentials. We don't have tetany in a neuron like we do in a muscle cell. We don't have a greater and greater and greater contraction. Remember tetany from the muscle cell. You increase the frequency of stimulus and the muscle cell contracts greater and greater and greater. Well, we don't get that in a neuron. Each action potential is exactly the same. And you can't pile a second action potential on top of the first one like you can with a muscle twitch. The nerve cell, the neuron has to have time to reset itself so it can respond again. So we have what's known as a refractory period. Refractory periods are events in our bodies where where a follow-up action can't occur. It's like the reset phase in our bodies. We'll discuss those in greater detail in AP2. So in a action potential, the refractory period is the time, I don't want to say after the action potential, but the refractory period is the time during the passage of the action potential that you can't have a second action potential generated. If you are in the phase of threshold up to plus 30, a second action potential can't come in while you're going up to plus 30 millivolts. When the sodium gates are open, you can't initiate a second action potential on top of the first one. And so we call this, there are two types of action, there are two types of refractory periods. The first one is the absolute refractory period. We can't get a second action potential on top of the first one because the sodium gates are already open. We have no sodium gates left to open up for another one. So we can't get a second action potential. So we say this is the absolute refractory period. The absolute refractory period goes from threshold to resetting. And from threshold to resetting means we go from threshold up to plus 30, back down to threshold. That's the absolute refractory period, from minus 55 to plus 30, back to minus 55. You can't get those gates to open up in that time frame. Sodium gates are already open, and even though we're closing them at plus 30, they're going to be closing from plus 30 all the way down to threshold. So we can only get an action potential when every gate is shut and reset, ready to go. So we know that makes every action potential an all or nothing event. Either all the gates open or none of the gates open. We don't get some of the gates to open. And it also means we send our action potential one way only, downstream. So the absolute refractory period is followed by the relative refractory period. The relative refractory period is the time where we can get a second action potential, but we have to have a more powerful stimulus to do it. Because in the relative refractory period, yes, we've got all of our sodium gates back into their resting position, and we're down below threshold. But remember here in the relative refractory period, we are hyperpolarizing now. We're going all the way down to minus 90. We still have to hit threshold for an action potential. But now in the relative refractory period, the charge in the membrane isn't minus 70. We have hyperpolarized down to minus 90. So now you have to be able to not have a stimulus that will get you to threshold from 70 to 55. Now you got to have a stimulus that can get you from minus 90 to 55. We can have a second action potential in the relative refractory period, but it has to be a very strong stimulus. We have to open up a lot more sodium. We have to stimulate a lot more neurons to fire their action potentials in here to respond at this point. Now, okay, so this is depolarization. You all know that. I've probably worn out the use of this animation. So with the absolute refractory period is this area right here. We start, the absolute refractory period starts at threshold, and we cannot get a second action potential to start in the area outlined in the blue box. So from minus 55 to minus 55. While we are depolarizing and depolarizing and depolarizing all the way to plus 30, we can't get a second action potential to form. Sodium gates, all the sodium gates are already open. We can't open anything else. We start closing those gates at plus 30, and the potassium gates start opening up, and potassium starts leaving the cell, and the charge in the membrane starts to drop and drop and drop and drop. This buys us the time to reset the sodium gates so we can do it again. And we will reset our charge in the membrane all the way down to minus 55. But we will undershoot. We will shoot all the way down to minus 90 and then come back up to minus 70. Now remember that what's happening at this point, let me bring up the relative refractory period in here. We are, when we repolarize, we are changing the charge back to normal on the membrane. We're going, remember the membrane was initially positive on the outside and negative on the inside. When we depolarize, we make the outside negative and the inside positive. When we repolarize, we bring it back to what it was before. We put positive ions on the outside and negative ions on the inside. But the problem is we've got potassiums outside and sodium's on the inside. What good is a sodium gate going to do if you already got sodiums on the inside? So what happens in that green box there is not only do we have to reset the sodium gates and reset the potassium gates, but we have to use the sodium potassium pump not to get the ions in the right places again, which we do. And if we have a strong enough stimulus, we can take advantage of the fact that the ions are being put back where they belong. The charge on the outside of the membrane is still positive. Charge on the inside is negative, but we better have a very powerful stimulus to get a second action potential. We generally are not, we cannot get a new action potential on the first part. We might be able to get a second one in the second part of the refractory period, but it depends on whether or not the sodium levels have been put back where they belong, if all the sodium gates are reset or enough of them are reset to do something. So absolute refractory period, no second action potential. Relative refractory period, maybe. So to summarize the action potential in the neuron, resting potential is -70. Threshold is -55. It's only 15 millivolts. It's easy to get the threshold. The neuron is much more sensitive than the muscle cell. We depolarize from -70 to +30 when we hit threshold. We go all the way up to +30, and then we go back down to -70. But there is that little undershoot there where we go down to -90 and we're hyperpolarized, which buys us the time to finish resetting everything. Now, where do we get our depolarization events taking place? Well, we know that our localized depolarization events take place on the dendrite. Because the dendrite is where the sensory receptors are located. It receives the dendrite is going to receive the information from the sensory receptor. Perhaps the dendrite is the sensory receptor. A touch receptor is stimulated because you've deformed the dendrite and you have a localized depolarization event. And it spreads down across the cell body, from the dendrite to the axon hillock. You form your action potential starts at the axon hillock when you depolarize the threshold. And then it runs all the way down the axon to the axon terminal. Now, what's going to happen next? Well, you're going to have to connect indirectly to another neuron, to a muscle cell, or to a gland. You have three choices: another neuron, a muscle cell, or a gland. And we send information in our brain. We're going to go, and in the spinal cord, we're usually going to go neuron to neuron to neuron. Now, the connection between the neurons, like the connection between muscle cells and glands, is what we call the synapse. The synapse is the indirect connection of a neuron to another neuron, a muscle cell, or a gland. They're not hardwired. Just like the motor end plate at the neuromuscular junction is not touched by the axon terminal, but depends on neurotransmitters to be released from the axon terminal to land on the motor end plate to open up sodium gates. We have the same principle taking place here at the synapse. A neuron that is carrying an action potential down to its axon terminals will not touch another neuron. The gap there is a gap between the neuron, what we call we call it the presynaptic neuron. There's a gap there at the synapse. There's a synaptic cleft in between the presynaptic, what we call the presynaptic neuron, and the postsynaptic neuron, meaning the upstream neuron and the downstream neuron. So when we're going to connect from one neuron to another, the upstream neuron is sending its action potential down to the axon terminal. The downstream neuron has dendrites waiting for it. And we will release a neurotransmitter from the axon terminal of the upstream neuron, which will open up sodium channels or potassium channels, or close sodium channels or potassium channels on the downstream side. It just depends on what kind of neurotransmitter it is. They're not always going to be excitatory. Acetylcholine is excitatory in skeletal muscle. You release acetylcholine into the skeletal muscle, it opens up sodium gates, and the muscle depolarizes, and you get an action potential, and the muscle contracts. But in the heart, in cardiac muscle, acetylcholine doesn't cause a contraction. It doesn't stimulate the heart, it slows it down. Same neurotransmitter, but here its role is inhibitory. It slows things down. So the proper term, presynaptic neurons. It is the neuron, the upstream neuron that is delivering the action potential to the synapse. The synapse is the indirect connection of the axon terminal and the dendrite of the next neuron. The postsynaptic neuron is the downstream neuron. It's the one that's going to receive the information and regenerate the action potential. So when we connect neuron to neuron, we have an axon terminal on the upstream neuron and a dendrite on the downstream neuron, and that's where the synapse is located. There's a little gap there. So we have, the proper term is the presynaptic neuron and the postsynaptic neuron. The neuron above the synapse, the neuron below the synapse. Now, where do we have connections? Well, we generally see our synapse. I want to move you out of the way. There we go. We generally see the classic type of synapse that we're all familiar with is axon to dendrite. Axon terminal, those green things up there on the picture are the axon terminals, and the red stuff moving down is the action potential, and I guess the yellow is the neurotransmitter, and we're connecting axon to dendrite. We're synapsing at axon to dendrite, and we're using the neurotransmitter. We don't know what the neurotransmitter is. There are 60 different neurotransmitters. Some are excitatory, some are inhibitory, some are both. We can also connect axon to cell body. Down here is the axon going to the cell body. It happens. Sometimes we throw a curve and we go axon to axon. That can happen too. Sometimes we go dendrite to dendrite, and sometimes we go dendrite to cell body. So there are very few combinations that don't work. Just about any combination of connection can work here. But the most common type, bless you, the most common type is axon dendrite. Now, there are two types of synapses. There's electrical and there's chemical. Most of our synapses are chemical. There's only a few places where we have electrical synapses. They're faster. They're a lot faster, but they're only in a couple places. The electrical synapse uses a gap junction to communicate. You remember gap junctions are the openings in the cytoplasm, in the membrane of adjacent cells. And so the cells are butted up against each other and there's a hole between them so we can communicate back and forth right through there. Electrical synapses work that way. They go through these gap junctions. We have very rapid communication. We find this in eye movement. Controlling the muscles around the eyeball. There are 6 muscles that surround our eyeball. And controlling the movement of our eyes is done through electrical synapses, very rapid movement. We also use this for tying in memories and emotions. Memories can trigger emotional responses suddenly. It's because the area of the brain that deals with storing emotion, storing memory, is also, we have it linked to our emotional memory too. So you think of some event that was pleasant and you feel good, or you think of some event that is sad and you feel bad, and it can occur instantly as far as we're concerned. And it's because of these electrical synapses occurring in the brain. Those are about the only places we see electrical synapses. The rest of them are chemical. We use neurotransmitters. Acetylcholine is just one of the neurotransmitters. There's a lot of neurotransmitters, about 60 different neurotransmitters. Now, just like in the muscle cell, the axon terminal has synaptic vesicles that contain different types of neurotransmitters, and depending on the one we're going to release, when we get, we're going to let the vesicle, when calcium enters into the axon terminal, just like in the muscle cell, the action potential comes down the neuron, comes down the axon, voltage gates open up for sodium. That allows the synaptic vesicles to fuse with the membrane of the axon terminal, and the neurotransmitter is released into the synaptic cleft, and it drifts across and lands on the dendrite on the postsynaptic side, and the neurotransmitter does something. It opens up a chemical gate, or it closes a chemical gate. So it drifts across to the other side of the synaptic cleft, and then we open up sodium channels, or we open up potassium channels, or we close potassium channels, or we close sodium channels. So the synaptic cleft is very important. We don't want to be hardwired. The synaptic cleft is a built-in delay to make sure that the postsynaptic neuron is ready to receive essentially the new action potential. It is a reset. It gives us a reset there so that we have an action potential that has generated in the postsynaptic neuron. Now we're ready for another one. And so the delay built in by the synaptic cleft guarantees that the postsynaptic neuron is always going to be ready for another action potential. So if we were hardwired, we wouldn't have that delay built in. We might not be able to we couldn't guarantee that the postsynaptic neuron is ready. Plus, it would also give us a direct passageway back up the axon to the brain. If we were hardwired into the postsynaptic neuron, something that would be moving back up the axon could make the leap. Well, there wouldn't be any leap. It could just go right through where the synaptic cleft should have been and on up in the presynaptic side and up into the brain or spinal cord. So we don't want to have two-way travel. We want to have it to go one way. It's going to make funny noises if I don't turn the volume down. There we go. Okay. Now the neurotransmitter will diffuse across the synaptic cleft and land on receptor sites just for that neurotransmitter. These ion channels that it lands on are going to do something. They may open, they may close. What's going to happen is we will generate a graded potential on the postsynaptic side. Because if we open up an ion channel, ions will come in or go out. We will do something to the charge in the membrane. If we generate a graded potential, will it be strong enough to hit threshold? Well, if we're receiving an action potential from the presynaptic side, then we're probably going to have a gradient potential strong enough to open up an action potential on the postsynaptic side. But in either case, we can be excitatory or we can be inhibitory. We're not limited to, well, we're always going to excite the postsynaptic neuron. So. Restart.
An action potential arrives at the end of the axon of the synapse.
Here we go.
There is a narrow gap, the synaptic cleft, between the synaptic terminal of a sending neuron and the surface of a receiving cell. An action potential arrives at the end of the axon of the sending cell. This causes chemical changes that make vesicles containing a chemical called a neurotransmitter fuse with the plasma membrane. The neurotransmitter molecules spill out into the synaptic cleft, diffuse across, and bind to the receptors on the receiving cell's membrane. The binding of neurotransmitters to receptors causes the attached ion channels to open. Depending on the type of neurotransmitter, receptors, and channels involved, this may excite or inhibit the receiving cell. Here we show excitation. Sodium ions rush in, changing the polarity of the membrane, and an action potential is triggered in the receiving cell. The neurotransmitter is broken down by an enzyme, and the ion channels close. Enzymatic breakdown is one of the several mechanisms by which transmission is terminated at chemical synapses.
So depending on what the neurotransmitter is, we have to break it down. We have to get rid of it so we can do it again. Acetylcholine gets released into the synaptic cleft in skeletal muscle. If we don't get rid of it, the muscle never gets a chance to contract again. The acetylcholine is keeping the sodium channels open. Sodium continues to rush in. We continue to depolarize, keep the motor end plate depolarized, and so we have an action potential that we can keep generating it. If the acetylcholine wasn't destroyed, the action potential in theory would could still occur. Your muscles would be immobilized. Or if we destroy all the acetylcholine, we could never get another contraction. You know, too little breakdown of the acetylcholine means there's too much there. We stay contracted, we're tightly contracted. Too little means we never contract it again after the first one. We're destroying the enzyme. So anyway, we got to get rid of whatever the neurotransmitter is in the synaptic cleft so we can do it all over again. Now, here is an animation of the presynaptic neuron and the postsynaptic neuron. This is typical action potential coming down the neuron, coming down the axon. You'll see sodium coming in, you know, it's depolarizing as it goes along. It's all dumb and happy, just coming right along. Calcium opens up, the neurotransmitter fuses with the membrane and gets released across the synaptic cleft and lands on the postsynaptic neuron, and everybody's happy. So the delay here is about 1/2 millisecond. So here comes our depolarization wave. There goes the calcium channel opening up. We fuse with the cell membrane of the presynaptic neuron's axon terminal, and neurotransmitter lands on the postsynaptic side at a receptor site. 1/2 millisecond delay. And that's all it took, was to make sure that the postsynaptic side is reset, ready to go. Now, what happens on the postsynaptic side? Well, it depends. Depends on what the neurotransmitter is. Depends on whether or not it's reset. If the delay was long enough, it usually is. You know, the synaptic delay can last up to 5 milliseconds, 5 thousandths of a second. We can't comprehend something that short. It can be as little as 3/10 of a thousandth, whatever, of a second. 3/10 of a millisecond, whatever. Anyway, it's very, very quick. So the synaptic delay slows down the transmission of the action potential from the presynaptic side to the postsynaptic side so that the postsynaptic neuron is ready to go. And we don't notice it. We don't see any delay, but it's there because everything downstream is working like it's supposed to. Now, depending on what happens, depending on what neurotransmitter that's released and its effect, we're going to generate a graded potential that does, a graded potential is a charge on the membrane. It's a change in the charge in the membrane. We can depolarize. Don't think that a graded potential is always a localized depolarization. We can depolarize the downstream neuron, localized depolarization of the dendrite, or we can hyperpolarize the dendrite. That's still a graded potential. Because again, it's a change in the charge. Now, the two types of potentials that we can generate are what we call an EPSP, the excitatory postsynaptic potential. In other words, we get the postsynaptic neuron excited. It means we have a graded potential that is a localized depolarization event, and we're getting closer and closer to the action potential. That's an excitatory event. Or we have an inhibitory postsynaptic potential. The charge in the membrane is -70. Well, we're driving it up to -90 or down to -90. So we're moving further away from an action potential. We can either inhibit the chance of an action potential, or we can excite the chance of the action potential. Inhibitory moves us away from threshold. Excitatory moves us towards the threshold. So this is the excitatory. This is the EPSP. This is the local depolarization of the postsynaptic membrane. This is a graded potential. It's getting us, as we release more and more neurotransmitter into the synaptic cleft, we're opening up sodium channels. We are depolarizing more and more regions of the dendrite, and we're getting us closer and closer to threshold at the axon hillock of the neuron. And so we are going to bring us, if we have a sufficient stimulus, we're going to hit threshold. This is the excitatory side. The inhibitory side is hyperpolarization. The charge in the membrane doesn't go towards threshold, it goes away from threshold. We drive us towards the other way. We are opening up potassium gates. Instead of opening up sodium gates and depolarizing the membrane, we are hyperpolarizing because our neurotransmitter is opening up potassium. So we're going further and further away from threshold. We don't want to get excited. We're dull, we're boring. We want to stay inhibited. So we're over here on the inhibitory side. The more potassium we have, the further away from threshold we get. The charge, instead of being at -70, is being driven very nicely towards -90. So now, instead of only having 15 millivolts to get the threshold from 70 to -55, now we're all the way at 90 to get to 55. So we are either going to be excitatory or inhibitory. So here we see, here is your synaptic cleft with your presynaptic neuron up here and your postsynaptic neuron down here. And this first one's going to be excitatory because we're going to allow sodium to come into the postsynaptic neuron, and sodium always depolarizes the postsynaptic neuron. So here comes sodium, here comes sodium, here comes sodium. Calcium gates open up, we fuse, and there goes the neurotransmitter, likely acetylcholine, but it doesn't have to be. Sodium rushes in, and we are depolarizing our postsynaptic neuron, and we are heading towards threshold. And so we're all happy. we've got an action potential likely forming in the postsynaptic side. That's the excitatory, the EPSP, the excitatory postsynaptic potential. What happens if it doesn't do that? What happens if we go the other way? We know what happens with sodium. We get, we can depolarize and we get the threshold at the axon hillock of the cell body. The dendrites localized depolarization gets down to the axon hillock. We hit threshold and we've got an action potential, and it runs all the way down the downstream neuron all the way to its axon terminals. But what about inhibitory? With inhibitory, we're going to do the opposite. Instead of getting us closer to an action potential, getting closer to threshold, our neurotransmitter this time doesn't let sodium come in, it lets potassium leave. And when potassium leaves the cell becomes hyperpolarized. The charge in the membrane goes from -70 to -90 or greater. So we don't, and this is a different neurotransmitter. So here comes the action potential upstream, calcium sodium neurotransmitter goes over, lands on the postsynaptic neuron, and it opens up potassium gates that allow the potassium to leave. And the charge on the cell, on the postsynaptic neuron, goes from -70 to -90. It's much harder to reach threshold. And sometimes that's what we want. Sometimes we want to get further away from threshold. So you have two options. You either can get closer to threshold, the EPSP gets you closer to threshold, or to threshold, the IPSP takes you further away. Now, in both cases, though, you have to get rid of the neurotransmitter. Here we have our presynaptic neuron releasing its neurotransmitter, and it gets released, and it can't land on its receptor site because something's already there. This is why we have to get rid of what's already in the synaptic cleft. The receptor site is blocked. We can't get there. It's already filled up with the old neurotransmitter. So before we can release more neurotransmitter, we've got to get rid of what's already in the cleft. We use the enzyme acetylcholinesterase, or just cholinesterase. It's shortened, you save 5 letters by saying cholinesterase. We destroy, the enzyme breaks down the acetylcholine, so we can do it again. There's a whole category of insecticides that kill bugs, but because the chemical is what we call a cholinesterase inhibitor. In other words, the enzyme that normally breaks down acetylcholine in the bug's muscles is inhibited by this pesticide. You spray this stuff on them, excuse me, and they die. Their muscles contract and they die because they can't have another contraction. The cholinesterase is being destroyed or blocked. And so the little bug muscles contract once and don't contract again, and your bug dies. So, and it works. Unfortunately, it also does the same thing to people too. If you were to accidentally get sprayed with a pesticide, an insecticide that was a cholinesterase inhibitor, then your muscles would contract and you'd die. So you die looking like a bug. So anyway. Now remember the term summation. Summation was what we talked about in muscles, where we add muscles, we bring more and more motor units together to get, to control the strength. Well, summation just means additive. And so we can have an additive effect to get more neurotransmitter into the synaptic cleft. We have summation through space. We have summation through time. Spatial summation means that we can use multiple axon terminals from a variety of neurons to release more and more neurotransmitter into the synaptic cleft, so that we have enough neurotransmitter to reach threshold or go further away from threshold. So spatial summation means that we have an axon terminal and another axon terminal and another axon terminal and another axon terminal. You can see the individual arrows on the screen, each one representing a different axon terminal, all releasing the same neurotransmitter, all landing on the postsynaptic neuron, all causing a depolarization or a hyperpolarization event. We didn't have enough, we needed more neurotransmitter, and we get it by sending out the signal to multiple axon terminals, all releasing the same neurotransmitter. And so we get some sort of graded potential on the postsynaptic side, either excitatory or inhibitory. Now we can also do it over time. Spatial means we have lots of axon terminals firing at the same time. Temporal summation, we send out multiple signals to the same axon terminal, and we release more and more neurotransmitter. It gives us the same effect. We want to get a lot more neurotransmitter to the postsynaptic side. Doesn't matter what we're trying to do. I mean, it does. Are we trying to hyperpolarize or depolarize? Whatever our goal is, we can accomplish it by sending out multiple signals from the same axon terminal. We don't know the difference. We can't tell this. Oh, I think I'm hyperpolarizing right now. We don't know. This is temporal summation. We have an additive effect over time, as opposed to spatial summation and additive effect over space. So when we have summation taking place, oh, my spider is back. So when we have summation taking place, we have three outcomes. We can generate we can generate a partial ESP. Oop. We excited the postsynaptic neuron, we depolarized the postsynaptic neuron, but we didn't get the threshold. We got to -56. We don't get an action potential at -56. We have to get to -55. We've excited the postsynaptic neuron. We have generated a localized depolarization event that's almost there, but not completely. That's one of the outcomes. The second outcome is, of course, we get an action potential. We actually hit threshold. We had enough neurotransmitter landing on the right spots to depolarize to threshold, so we get an action potential. The first choice was so close, but it didn't count. Just 1 millivolt away. Too bad. You get a participation trophy. Of all the EPSPs that ever occurred, you were one of them. So that's your participation trophy. But if you hit threshold, you get an action potential. The third possible outcome is that you end up being hyperpolarized. So you either depolarize but don't get an action potential, you depolarize and you get an action potential, or you hyperpolarize and you move further away from threshold and you don't get an action potential either, but maybe that's what you wanted. So these are the three possible outcomes you get from a summation. You know, and two of them are no. Okay, now let's move on. Okay, neurotransmitters. There's at least 50, maybe 60 neurotransmitters. We've heard a lot of discussion about acetylcholine. That is the most well-known of neurotransmitters. We know more about acetylcholine than any other neurotransmitter. We know that acetylcholine can be an excitatory neurotransmitter and an inhibitory neurotransmitter. It's excitatory in skeletal muscle. It's inhibitory in cardiac muscle. We classify our neurotransmitters both by structure and by function. Now, this is acetylcholine. It is a small molecule. It's released by the peripheral nervous system neurons and the central nervous system neurons. It's released at the neuromuscular junction. It is excitatory at the neuromuscular junction in skeletal muscle. It is inhibitory in cardiac muscle. It can be excitatory or inhibitory on smooth muscle. And it is broken down by the enzyme acetylcholinesterase. We have to take it out of the synaptic cleft. Whatever we're using it for, we have to remove it every time so that we can have a new action potential being, or blocking an action potential being generated. Okay, so, and that's a great place to stop. We will pick up with this on Tuesday and wrap up this chapter on Tuesday, and we will move into the brain and spinal cord. We'll probably start that on Tuesday because we've only got, let me see how many slides we have left here on this. We've got, oh, we got like 12 slides left. So I'll finish this easily on Tuesday morning, and we'll go into the brain and spinal cord then. Okay. Lab next week. I'll just remind everybody now that it's going to be dissection hands-on for those that are here in the class on Tuesday, and the class on Monday will get to watch it. So I'll be doing the cutting. Anybody have any questions before I get us out of here? Okay.